next couple of slides. So then it evolved to force-based design method, which is currently also the method in IS 1893 2016. The advantage of this method compared to gravity or the first method is that it gives some rationalization about the earthquake forces those are coming onto the structure. However, again, even there is advantage. The disadvantage is that these methods wouldn't actually contribute or doesn't actually comment on the actual capacity and actual deformation that is happening onto the structure. So then we have moved to first generation performance-based design. These started developing from the year 1995 to 2010. These are now getting accepted in advanced countries like USA, particularly in California region, where there is high seismic activity. And then there is a need to define for a certain level of performance, which is the condition of building after an earthquake. But even with this development, there are certain things which are not addressed at this moment, which are like if there is an earthquake, what is the possible loss in life, or what is the possible financial losses that could happen to the society. Because you need to understand that nowadays infrastructure, the role of infrastructure is not only to connect the people, it also has a great role in economic growth of the countries. So if an earthquake type scenario or earthquake happens, then the infrastructure get damaged, and because of that there are large economical influences or large economical consequences. So it is kind of the situation that we are experiencing in these difficult times of COVID, where we have seen that even though the lockdown or things are important in the point of view of restricting the COVID, it has very severe impacts on our economy. So similar situation, you can relate it to the earthquake, which is again a rare event. But if it strikes and if it damages your infrastructure, that could significantly hamper our economy, and it could cause us a significant losses, not just to building our infrastructure, also to businesses, and also it can affect social economy structure to a greater extent. So to address that, now there is a need of this second generation performance-based design. And whole this second generation performance-based design is based on the concept of risk. So that is why the study of risk is important. So before moving to the risk-based design, I'll quickly run through the force-based design and the performance-based design. So as you might know, the force-based design is the philosophy which is followed in IS 1893. So what we do in IS 1893 is we take up a structure, we figure out its natural frequency or natural time period, depending upon the type of structure. And using that, we figure out the lateral forces, those are coming onto the structure. So these are the typical steps that have been followed when you are designing a structure as per IS 1893 2016. These are quite familiar to you if you have already done the building design. So if you need to understand the philosophy of force-based design, which is the first thing after the Second World War, what essentially has done is we don't know the earthquake load characteristics, those are coming onto the structure. And because of that, what has been done is the entire building is idealized as a single degree of freedom system. And then for each single degree of freedom system, we apply a earthquake ground motion, and then we figure out its response. And then the peak response, which is typically the peak displacement response of a system, is being taken from that particular linear time history analysis, as we call it. And then we plot that peak response against the frequency or against the time period. Similarly, then we change the property of single degree of freedom system that lead to change in time period. And then we redo this process of applying time history and finding out the displacement response, and then figuring out the maximum response from each of the analysis. And then once we're done with all this analysis, then we plot the maximum displacement of a single degree of freedom system, which is we call spectral displacement, as a function of frequency or time period. So this is the spectrum that we get. It's called response spectrum for a single ground motion. Okay, now the funnier part is in case of earthquake engineering, even though we say we are designing for a earthquake, we are not sure about the characteristics of ground motion. Those are possible at given site or at a building location. So to get rid of that, what we do is we do this analysis for various ground motions, and then we do the assemblage and figure out the design response spectrum. Before that, the displacement that we got, the spectral displacement, is then used to figure out the acceleration and velocity. Since the acceleration and velocity are calculated based on the spectral displacement, and not by actual differentiation of spectral displacement, they are called pseudo acceleration and pseudo velocity, in which the acceleration and pseudo velocity are simply estimated as frequency from the function of frequency and the spectral displacement. So the spectral displacement has been converted into pseudospectral acceleration spectrum. And then, as I said, since we don't know the ground motion timescales which are coming onto the structure, we do this process of figuring out the pseudospectral acceleration for various ground motion, and then we plot them on 4-log paper, and then we take the average of those, and then there are methods to figure out the design response spectrum. This method is called Newmark-Hall design response spectrum, and the procedure is given in A.K. Chopra in chapter number 6, which you can follow to figure out the design response spectrum. So similar procedure is being followed in our IS 1893-2016, where the various regions in the country are defined in various zones, which provides you the level of hazard. And then the level of seismic force on each structure is calculated using design spectrum, which is a pseudospectral acceleration spectrum, which is a plot of pseudospectral acceleration on y-axis and then the time period on the x-axis. Again, there are additional issues in earthquake, which are called soil amplification. We will see in next couple of slides. And because of that, there is an additional amplification of force. So to account those force, the IS 1893 has given 3 types of spectrum for 3 types of soil: type 1, type 2, and type 3. Depending upon your type class and knowing the time period of the building, you can figure out the pseudospectral acceleration that is coming onto the structure. So IS 1893, basically, once you know the zone factor, which is depend upon the location of your building, you could figure out the acceleration coefficient. So in this expression, this term ZA by 2 gives you the is depend upon the zone factor. SA by G is obtained from these curves, which are the pseudospectral acceleration, and R is response reduction factor, which is again depend upon the inelastic characteristic of building, and I is the importance factor, which depend upon the occupancy type of the building. So this is the overall lateral force that has been calculated using IS 1893. Once you have the knowledge about the location of building, you can work out the zone parameter, and knowing the time period, you can work out the SA by G value. The important parameter, which is in this expression, is R and I. I again depend upon the occupancy type. So for regular building, the I factor is 1. For importance, it is 1.2 and 1.5 in new IS 1893. Then the important factor is R, and the reason I'm saying it is important because if you look out the expression, the R factor actually reduces the design seismic coefficient. So if you have higher R value, it means that the amount of force that is being used to design a structure is less. And if you have lower R, it means the amount of force that is being used to design a structure is large. So as your force is reducing, your building is more economical. And the reason we want more economical buildings, because earthquakes are very rare phenomena. But then the question is, how do we obtain this R, which is the response reduction factor? In addition to that, IS 1893 also mentions that the structure need to follow certain deformation pattern, that if earthquake strikes, it should follow that the beam should yield first and then column shouldn't have any kind of damage. And the reason for this is if the column fails, then we will have a severe collapse. And if the beam fails first, then we will get the sufficient warning, and it can still resist the earthquake force by a phenomenon which is called the energy dissipation concept. But even though code has mentioned that, how do we actually say that a certain building has certain value of R, which is a response reduction factor? So to figure out that, we need to understand the inelasticity of the material which constitutes the building. So in this presentation, I will be focusing only on reinforced concrete buildings. So in reinforced concrete buildings, the materials which are used to construct a building are two, which are steel and concrete. So this is a stress strain curve of the steel on the left hand side, where you can see that for a mild steel, there is an increase in stress, and then there is a yield point, and then it goes into the inelastic range. Likewise, if you increase the strength of the steel, the strength increases. However, the ultimate point reduces. So this is what happens when you use HYSD bar, which is the steel which has been generally used to construct the reinforced concrete buildings. So this is, if you look out the characteristic of steel reinforcement under axial tension, the stress strain curve that you might have aware that there is a yield point and then there is a inelastic property. Now, when you design a structure, you always ensures that all the forces are always below this yield point, and that is to ensure that your structure always remain elastic. However, when it comes to earthquake, since earthquake is a rare phenomena, we consider the capacity of the structure as well as of the material in the inelastic portion, which comes in this region. So this is the inelastic or the stress strain diagram of the steel. Likewise, this is the stress strain diagram of a concrete. This is different from the stress strain diagram of a concrete given in IS 456. In this figure, if you can recall, the unconfined concrete is very close to the stress strain curve of that of given in IS 456, while the confined concrete is the stress strain curve of the confined concrete is the one which you obtain if you put confined reinforcement as per IS 13920. So again, over here, if you look out the stress strain curve of the concrete, it has some linear portion, then it goes into non-linear range. When a steel bar is subjected to a cyclic loading, which is the magnitude of load if it is in the inelastic range, then what you can observe that the steel, the stress strain curve is actually a loop which is called a hysteretic loop. And when there is a force which is greater than the yield force, the structure, the steel bar gets into the inelastic range, and the additional force beyond the yield point is resisted through this energy, which is the area under this hysteretic loop. Now, this is for a single structural or reinforcement bar. Likewise, if you take a RC section or RC column, and if you apply a load at the top of that column, and if you increase the intensity of that load, then increase the intensity of that load and also change the direction continuously, then this is what you will get. This is called the hysteretic diagram of RC section, and it gives you that what is the possible yield point and yield load for this given RC section. And then as the load is changes its direction, then what is the amount of area which is enclosed in this hysteretic diagram. So why these parameters are important? Because if you know the ground motion time history of an earthquake, then you can see that it always go up and down, and then at the end there is no acceleration. So what it means that earthquake load is a cyclic load, and because of that, the forces which are coming onto the structure and the members are cyclic in nature. And at the end, since earthquake ground motion always stops after a certain time, because of that, the amount of force that is exerted is either in terms of displacement or in terms of the forces. And since we are designing the building for lower level of forces, the building naturally go into the inelastic range, and the behavior of member in that building is represented by this kind of curve, which is called the hysteretic curve. Now, even though we understand the inelastic cyclic behavior of the building, how can we use this to obtain the behavior of entire building? If we understand the behavior of the member, how can we use it to determine the inelastic behavior of the building? So to study that, we have a method which is called pushover analysis, which we will discuss in performance-based design. So once we do the pushover analysis of a building, we get a force deformation characteristic of a building. And based on that, we can figure out the ductility of the building, which is the ratio of maximum displacement that building can undergo to its ill displacement. And using this ductility, there are two rules which are given in the literature, which are called equal displacement and equal energy principle. Using these two rules, we relate the ductility to the R factor, which is our response reduction factor. Again, this formulation, whether it's to be equal displacement or equal energy, it depends upon the time period of the structure. So if you have a structure which is having a time period in the displacement range or in the velocity range, then we choose the R factor, which is equal to that of the ductility of the beam, ductility of the building, and this is called equal displacement rule. However, for shorter period buildings, we use equal energy principle, in which we say that the energy imparted by an earthquake for elastic structure has to be equal to the energy dissipated by a structure through inelastic displacement. So naturally, the R factor that is being used for structure which are having lower time period is lesser than the structure those are having larger time period. So that is how we figure out the value of response reduction factor. So the values of response reduction factor given in the IS 1893 helps you to reduce the forces which are coming onto the structure, and you reduce. So you basically design for a force which is very less than what is actually occurring on the building during earthquake. So this is the design response spectra given shown in the blue color, and then you apply the response reduction factor to obtain the obtain the design level forces. But once you do this, you ensure that when earthquake strike, your building gets into the inelastic range or inelastic response. So knowing all this mechanism and the philosophy of earthquake resistant design, IS 1893 says the expected performance of the structure is as far as possible for lower magnitude of earthquake to remain elastic. However, so that it means that there is no structural damage to the moderate intensities. However, there shouldn't be the collapse of the structure under heavy intensity earthquake. So it means that there shouldn't be the collapse, means that the structure shouldn't reach the ultimate point, but it is expecting that the building will reach in the inelastic range. So if you follow IS 1893 and if you design a structure, it is expected to have some damage to that particular building after a strong ground shaking. Can you see my screen?
Yes, sir.
Okay. So now imagine that in your city, if you are designing several reinforced concrete buildings, and if tomorrow there is an earthquake, then most of this building will get into the inelastic range. And since you are getting into the inelastic response range, you will have certain type of damage. Now, even though the building is not collapse, will you do your business, or will you stay in those kind of damaged building? That is the question. And IS 1893 doesn't answer that. Yeah. So yeah, let's see what is the possible situation happens to buildings. So let's say a group of building got hit by an earthquake, and those building get into the inelastic range. But then what is the situation of the building, even if it is damaged? So there are ways to classify the damage which is occurring in the earthquake. That is called damage classification. And it is generally being used to understand the strength of a building in post-earthquake situation. So here are some of the example of buildings after an earthquake. So the first stage is we call a building is in slight damage state, where the non-structural element or the windows and furniture of the building get disturbed entirely. However, there is a minimal damage to a structural system, which is shown over here. Likewise, there is minimum cracks or some cracks are experienced at the joint of the at beam column joints. Then the second type of damage that we experience or that we classify is a moderate damage, where most of the non-structural element suffers the heavy damage, but some of the structural elements also experience moderate damage. Moderate means you can see the reinforced bar exposed. There could be a significant spalling of a concrete cover at many locations. And these are the example where you can say that the building has suffered a moderate level of damage. Then the next is the collapse state of the building, where you can see that the building has changed its geometry. So the building is no longer vertical, it has a residual displacement. And once it has the residual displacement, there is a P delta effect, and the building is not advisable to occupy in any sense. Or you can have a pancake-like failure where the entire floor is getting disturbed. So these are the possible states of the building after an earthquake. And before sharing these photos, I ask a question that IS 1893 says that your building can suffer a damage after a significant earthquake. Now, which of these three states are possible? That is not actually answered by IS 1893. So if you could say that I want to eliminate the collapse state of the building, then the next question is, since the earthquake is very rare phenomena, we don't know its occurrence, we don't know the ground motions which it imposing onto the structure, what is the possibility of such kind of collapses? So if I rephrase this question and if I put it in different form, what I could say that if there is a building which is 8-story tall and having a plain regular plan, and if I design it as per IS 1893, what is the possible rate of collapse of this building when earthquake strikes? And this is the question that need to answer through risk targeted design and through performance based design. So to understand that, first of all, we need to understand what is the meaning of collapse. So far we have seen the inelastic characteristic of material. To some extent we have seen the inelastic characteristic of a building. But when we say we are choosing a R factor to reduce the amount of forces those are coming onto the building, what is the expected collapse mechanism, or what is the expected definition of collapse that we are saying? And then secondly, more importantly, how can we calculate the risk of collapse, or in other words, what is the rate of occurring such collapses in a building? At this moment, I'm talking only about the single building, but if you can imagine that if the situation of a single building is so uncertain, what could happen to a group of buildings which are located all across the same building? So quantifying the risk of single building is important to understand its performance, while understanding the behavior of large number of building is very important to understand the losses which are important, which are imparted by the seismic forces. So to understand, to quantify this philosophy, the first level performance based design comes into the picture, where the risk is expressed in terms of the variables which are useful for the decision making, in terms of, as I said, in terms of the seismic losses, and also in terms of understanding what is the risk of individual building. So to quantify this, the first level performance method has come up. So before moving towards that, are there any questions regarding the content which I have covered? Do you want to ask anything, or shall I continue with the presentation? Is it okay? It is okay to me if you have any doubts, you can ask at this point itself. Any questions?
No, sir.
Okay. So, as I said, uh, to understand the need of, to understand the collapse of a building and to understand the possible performance of the building, there is a evolution of earthquake resistant design, and that is what we call first generation performance based design. It started in 1996 with a report ATC 40, which is the Applied Technical Council of United States, and then they introduced the concept of performance levels. These performance level are, you can correlate it with the damage state that we have seen, which are slight, moderate, and the collapse state. So you can say that I can choose the performance level, and then I can choose whether my building wants to be either in slight damage state, moderate damage state, or in collapse state after a characteristic earthquake. So these procedure mainly help us to figure out the ductility and inelastic capacity of the building, which are useful to reduce the earthquake forces and also responsible for the condition of a building after an earthquake. I'm not entirely discussing these methods. I'll just give you the brief overview of these methods. So the good method for the first layer performance based design is published by Calvi in Model Code in 2009. Then the European code is there, which is a Model Code 2010. And then the latest one that we have is the ASC 41 2017, which gives us the procedure to evaluate the existing building and also to carry out the performance-based design of new buildings. Again, India doesn't have any standard to carry out the performance-based design. So these are the three methods available. So if you can understand that the force-based method is based on the extension of Newton's second law, where you can say that the forces which are coming onto the structure are proportionate to the inertial forces of the building and the earthquake acceleration. However, in these methods, you can idealize the earthquake ground motion as the displacement. It has been displacement that has been applied at various structural parts or at the various structural levels. So that is what the first document talks about, which is the displacement-based seismic design. Instead of designing a building for set of or specified acceleration, now the building has been designed for specified displacement. So the extension of a building is been considered when it comes to the first document, which is the displacement-based design. Again, the rationality behind this method is, even though we say that the forces developed are proportionate to the acceleration which is imparted by the ground motion, the forces are also proportionate to the stiffness time the displacement. So the displacement caused by the earthquake ground motion, the relative displacement caused by the earthquake ground motion, is very peculiar characteristic peculiar characteristic for designing of the buildings. So in these methods, again, the formulation is changed from force based to the displacement based. And in addition to that, instead of designing only for collapse state of the building, now you can choose whether it to be designed for various performances like immediate occupancy or life safety or collapse prevention. Again, these three performance level, even though their name is different, they are similar to the slight, moderate, and collapse damage states that we have seen, which occurs after an earthquake. So you can figure out what is my target situation after an earthquake, and depending upon that, you can choose the displacement which are coming onto the structure, and you design a structure for that particular design demand. So these are the typical steps in the performance-based design. Since in this method, we are not designing for the forces, we are designing for the displacement. We need to understand the inelastic characteristic of each individual building. In the force-based design, we ignore the understanding of inelastic characteristic of the building, and we simply take up the parameter R, which is a response reduction factor, to reduce the forces. However, in this method, since instead of force, we are relying on the displacement demand, we need to figure out a method to find out the ductility or the energy dissipation capacity of each individual building. And for that, the mathematical modeling or the analytical modeling is very important. And once you get the inelastic response, because you are modeling the structure for inelastic response, then you use the acceptance criteria, which is given in these methods, to figure out the sizes of the member. So there are various procedures. Again, like force-based method, it's not only one method available. There are many methods available. The popular one is capacity spectrum method, then target displacement method, and the displacement modification method. These are available in these documents, which are given over here. You can refer if you are interested in this method. For today's discussion, I'll be discussing only the philosophy of capacity spectrum method and its limitation. So, as I said earlier, depending upon the type of building, you could choose the level of performance. Now, when I say a type of building, you need to understand that if you are staying in a building which is a residential building, you could afford to say that I could design for building state which is equivalent to slight damage after a severe earthquake. But that would cost a lot of money, because you need to make sure that your building has sufficient strength and stiffness to resist large earthquake forces. So it's not economical viable to design each and every building for a very good performance level, means lower damage states. Thus, there are risk categories which are defined. So the risk category 1 and 2 means the general buildings, where you can say that building should have moderate damage when it comes to moderate earthquakes, and it should have severe damage or collapse state when it comes to severe earthquakes. Then the important buildings like hospital is categorized as risk category 3, where you could say that the building should have damage between slight and moderate state under moderate earthquake, and between moderate and collapse under severe ground shaking. And then the fourth one, which is very important structure like power plant, nuclear power plant, you could say that those buildings should always remain functional, like they shouldn't have any kind of damage or slight damage under moderate earthquake, and should have some kind of inelasticity between slight and moderate damage under severe shaking. So these kind of target definitions have been set up in these standards. And depending upon the level of hazard, you can choose up this performance building performance level, and then you design and ensures that your building is meeting this performance level. Again, the hazard definition that we are seeing here is what we call the probabilistic definition, and I will discuss that once we discuss the concept of risk. So, as I said, it's very important in these methods to understand the actual deformation capacity of the building. And for that, the method that is being followed is pushover analysis. So what we do in pushover analysis is we make up a building model where all elements of the building, all structural elements of the building are modeled using a line element, or there are many ways to model that as well. And then inelastic property of those elements is modeled using concentrated plasticity hinge. And then we apply an incremental load to this building, incremental load or incremental displacement. And then we push this building in one direction. And as we push, we measure the amount of forces that is being generated at the base, which is the base shear. So as you are pushing this building, you are applying the displacement, and then you are measuring the reaction, which is the base shear at the bottom. So this is what you will get, which is called a pushover curve. Now, this curve is important because as we have seen, like materials, now this is our capacity curve of a building, where as you see it is linear to a certain point, and then it gets into the non-linear range. So till the point it is linear, we call it as the linear response. And once it gets into the non-linear range, we say it's an inelastic response. Now, once we figure out the yield point at which there is a change in slope, that is my yield displacement. And likewise, the displacement at which my building stop providing any resistance is my ultimate displacement. So relationship or the ratio of ultimate displacement to that of the yield displacement is called ductility. So from this figure, we will figure out the ductility. And we have seen previously that there is a relationship between the ductility and the response reduction factor. depending upon the time period. Again, time period is depend upon the structural configuration, or you could use the formula which is given in IS 1893. You can relate this ductility to the response reduction factor. So that is one way to look at it. Other way is in capacity spectrum method. What it does is, now knowing the capacity of the building, which is shown in the red color, and knowing the demand as we have seen is estimated from the linear analysis. So it doesn't account the inelastic characteristic of the building response. Now what happens is, if your structure is linear, it has this initial slope, the slope of this line, which is the stiffness of the building, and your time period is actually related to this initial slope of this line. However, as structure get damaged, this secant stiffness reduces, and as your stiffness reduces, your frequency reduces, and your time period increases. And if you can recall the design response spectra, you can see that as your time period is increases, your force level reduces. Now, both these, when earthquake strikes happening at the same time, that your structure is getting damaged, and because of that, your demand is reducing. But when you are analyzing linear structure separately and non-linear structure separately. So the capacity that you got is the true capacity for given force distribution load, but then the demand that you calculated is for linear structure. So the only way this demand can be reduced is by considering the energy dissipating capacity of the structure, which is obtained through a formulation given in ATC 40. So basically this demand spectrum that you have is reduced to a level considering the energy dissipation capacity of structural members. And when this demand spectrum shown in the blue line intersect with the capacity curve, which is obtained from the Pusher analysis, you get a point, intersection point, which is called the performance point. And depending upon the spectral displacement or displacement demand at that particular point, you could figure out the forces, you could figure out the possible damage state of the structure. Now, if the spectral displacement is in the range of moderate and severe, you can say that the structure has crossed moderate and it has reached severe. So it means that only severe state is satisfied. The moderate state is not satisfied. So if you want to improve your performance, or to improve reduce the displacement at performance point, you need to increase your capacity. So if you increase this red line, it will cross somewhere here, and that's how you can reduce the spectral displacement. This is the general procedure which has been given in first level performance based design. Having said that, these are the general philosophies which are given in the code. But is it the really case? We have seen the possible damage states of the building after an earthquake. However, if you know the basis of earthquake, what happens during an earthquake is there are several faults which are located all across our Earth hemisphere. And one of those faults, when it slips, then it generates the earthquake ground motion. But as we all know, the location of these faults and the amount by which it slips is very unknown. So the amount of forces, those are coming onto the structure, as I said, in form of ground motions or in form of the displacement motions. We are not very sure how to obtain those. So the seismic load or demand that we are talking is uncertain, because at the moment the code provides us a single value, and it has been calculated by certain amplification factor which are estimated in the 1960s or 1970s, which is the Newmark-Hall method. So the seismic load is highly uncertain, and your resistance is also uncertain. Now, why I'm saying resistance is uncertain, we will see that in the formulation of risk. Now, in addition to that, as I said, since the response is inelastic, the resistance or the capacity of the building also depends upon the load characteristic. So there are two types of uncertainties: uncertainty of load, uncertainty of capacity, and both these uncertainties are related. That's the reason you can't estimate those separately. That is what given in first level performance based design, which we have seen in the previous slide. So how do we address that? That when load is coming, the structure is getting into inelastic range. In addition to that, we don't know the type of load, we don't know the characteristics of the load, we don't know the capacity of the building. How can we address that? And for that, the topic that we have chosen is important, which is the risk, the meaning of risk. So the typical definition of engineering risk is the relationship between the probability or frequency of undesirable outcome and measure of the degree of undesirable outcome. So the risk is defined as the product of probability of occurrence and consequence, probability of consequence arising from that particular occurrence. So to understand this definition of risk, we need to brush up our concepts on the probability. So I will start with this different subject altogether in today's discussion, which is the probability. And again, I'll be coming back its application to earthquake engineering. But before we come to that, first of all, let's understand what is probability and why we are saying the occurrence is so much of importance. So I hope all of you are aware the axioms of probability. The axiom says that if there is a sample space and if there are two events, E1 and E2, then probability of any event happening is always lies between 0 and 1. The probability of sample space is always 1, and the probability that both these events occurring is either the sum of these probability of these two events or the sum of probability of these two events minus the intersection part. This is again the mutual exclusive if these two events are not intersecting. So these are the axioms of probability. We need to understand that clearly, that probability is never going to be 1. When the probability is 1, it means that the event is happening for sure. When the probability is 0, it means that the possibility of happening that event is 0. It means that the event is, it's impossible to happen that particular event. Then there are sub laws. I hope all of you are familiar. So if you know the probability of event E1, then probability of E1 complementary is simply 1 minus the probability of E1, which says that if E represents event which is happening, then E bar represents the probability that event is not happening. Likewise, these are the other law where probability of phi, which is a null set, has to be 0, means it's an impossible event. In addition to that, you also need to understand the concept of conditional probability, where it gives us the probability of event E1 occurring after event E2 is equivalent to intersection of these two events, probability of intersection of these two events divided by the probability of event E2. So what it means that the probability that certain thing like a seismic damage happen after a ground motion is depend upon first the probability of happening a ground motion, which is event E2, and then probability of happening certain type of damage because of that ground motion, which is probability of E1 intersection E2. Okay, so these mathematical terms, you know, many of you have already seen that, but you need to apply that in terms of the seismic resistant design, or if you could elaborate that, then any kind of catastrophe event. Okay, so if I say that E1 is my probability of reaching any damage state and E2 is probability of happening occurring ground motion, then this gives me the possible probability of happening that particular damage state. Okay, now this is very important when it comes to seismic risk design. Then the next theorem, which is very important, is total probability theorem, which gives you that probability of happening A, because in various different events, is obtained using this particular formula, which is again the extension of conditional probability. And why this is important? Because in lifetime of a structure, even we say that we are designing for one particular earthquake, there could be another earthquake, even though its intensity is less, is also possible. So here E1, E2, E3 represents the possible earthquakes that could cause damage to a structure, then it couldn't be the same damage, the collapse damage. It could be some other state of damage as well. But even if we say it's a collapse damage, then there are various earthquakes which are contributing to cause the collapse of earthquake, and the total probability of happening A, which is in our case the happening collapse of a structure in given time, is again depend upon the combination of intersection of these various events and that of the seismic capacity, collapse capacity. Then the third rule, which is important in seismic risk, is called Bayes rule. Again, even though it is important, I'm not covering this in detail. This is particularly important for understanding which earthquake or which earthquake source can contribute maximum collapse of the structure, collapse probability of the structure, or this has been widely used in seismic hazard calculation to figure out which seismic fault is causing the maximum seismic force into the structure. This is available in many literature. I can also send you this PPT, which you can refer afterwards. If time permits, I will explain the use of or the application of Bayes rule. But at the moment, we will be focusing more on the total probability theorem, where we are calculating the probability of A. A in our case is finding out the collapse risk of the building under various earthquake scenarios, which are E1, E2, and EI, basically. Okay, so this is the background of probability. Now, even we say that we know the concept of probability. I have also briefed how we can use it for collapse risk. I will explain it in more detail in coming slides. But are we new to the variation in material strength? I explained earlier that there is an uncertainty in capacity. How do we estimate capacity of a building? Or let's simplify it further. Let's go back to the experiment that we have all done in our 12th standard, which is to figure out the modulus of elasticity of a wire, of steel wire or any kind of wire. So this is the apparatus that we have used. I'm sure all of you are familiar with it. So what we do in this to figure out the modulus of elasticity, we figure out the stress-strain relationship, and then we figure out the slope of line which is connecting all those relationship, all those stress-strain points. In this particular experiment, we apply load here, then we measure the strain in the wire, and then we figure out the stress depending upon its area. And then we keep on increasing this load, we keep on increasing the strain, and we keep on calculating the stress. So this is the procedure that we have followed. The slope that we get is the modulus of elasticity, and this is the experimental data that we have. Now, if you can see that the line fitting that we do, for this blue dot represents the experimentally measured points, and then the line fitting that we do is not actually covering all the points. Now, does it gives us the exact modulus of elasticity? Is the question needs to be answered when it comes to figuring out what is the meaning of collapse or what is the meaning of probability of collapse. So in this simple experiment also, if you can check, we all have done this, that the stress and strain relationship, even though mathematically it should follow a straight line, the points are not lying, all points are not lying on the line, the straight line or the modulus of elasticity line. Some points are above it, some points are below it. Now this, so the reason for this is the modulus of velocity that we are idealizing is through certain formulation, which is the ratio of stress and strain. However, the actual relationship between stress and strain doesn't need to follow the straight line. So there is a variation of this modulus of velocity at various stress and strain points, which has been represented by a function which is called probability distribution function. Now, let's say if I got this modulus of elasticity from this experiment, And now the same steel element, if I use as a rod, and if I apply load P to it having cross section A, the deflection that I will get, will it be a single value or will it be a different value? Because again, modulus of velocity is not the actual value that I'll be using. So how do we estimate that? This formula, which we all know for axial deformation, will it give me a single value or will it give me a different value if your value of E is not fixed? So that is the question that needs to be answered. And for that, you need to understand the variation of material strength. So if you can understand that when you fit a line to the experimental data, what you do is you find out the error between the observed value and the predicted value. And then you do it for all different points. You do square of sum of all different these points. And then you minimize this error. That is called the least square approximation. And that's how you obtain the fitted modulus of elasticity. Having said that, even though it's a fitted value, it doesn't actually gives you the exact value. There is a possible variation of modulus of elasticity at each level. And this possible variation is represented by a function which is called probability density function. So on x-axis, you have the modulus of elasticity, and on y-axis, the probability of having certain value of modulus of elasticity. So this peak value is called mean when it comes to normal distribution, and it means that the probability that most of these points will have this kind of modulus of elasticity is very high or significant. So mostly when we use the modulus of elasticity from these experiments, it is always the mean value, but we mostly neglect the variation of that modulus of elasticity. Now, some of you might aware that we have already seen this kind of concept, or you will see in your curriculum when it comes to characteristic strength of concrete and steel, when you will learn, or when you learn more about the reinforced concrete building. If not, some of you might have already learned that in your undergraduate curriculum. So this is the variation of the modulus of elasticity. This modulus of elasticity, the variation, is represented through a random variable. And as I explained earlier, the function that we have is called probability distribution function, which gives us the possible variation of modulus of elasticity. Now, this is the formulation. The function here is the density function, and here it is called the cumulative density function. So the cumulative density function is obtained by the integration of the probability density function. So at any given point, if you integrate the area under the density function, you will get the cumulative distribution function. And since probability cannot be greater than 1, the density function has the limiting value of 1 and the upper bound value of 1 and lower bound value of 0. Typically, it has been observed that the most of the variation that exists in the world follows a distribution which is called Gaussian distribution. And since it has been observed very widely, it is also called a normal distribution. So this is the formula of finding out this normal distribution, where mu represents your mean strength or mean modulus of elasticity in this case, and sigma represents the possible deviation from the mean modulus of elasticity. So the formulation is available. There are many other distributions. I'm not covering that. Those of you who are interested in this can refer to any books in probability. The good book for this is Ronald Ross, Introduction to Probability and Statistics. So there are many distributions. I'm just sticking for today's discussion to normal and to some extent to a law of normal distribution. So this is the definition of normal distribution. So coming back to the question, now instead of having a fixed value of modulus of elasticity for a given bar and knowing the load and actual cross-sectional area, you could figure out the deflection. But now I'm saying that the modulus of elasticity is not a single fixed value. It is basically a random variable. What it means that it can take any value of the normal distribution. Now, how can I figure out the deflection in that case? So this is the formula that I know, which is obtained from the classical mechanics. And now knowing that my modulus of velocity is a random variable. How do I estimate the deflection? Now, since E is random variable, my deflection is also a random variable. So I need a formulation in which I can relate the mean and standard deviation of deflection to that of the mean and standard deviation of modulus of elasticity. So there is a formulation that if y is sum of random variable x1, x2 to xn, so y is here the dependent variable, x1, x2, xn are independent variable. And if we know the mean and standard deviation of these random variable x1, x2, and xn, we can figure out the mean of y using this formula, which is nothing but the same formula in which you put up the mean values. And then the standard deviation of y, which is the independent, which is the dependent variable, is obtained using this formula, which is again the sum of square of standard deviation of these random variable x1, x2, and xn. So if you want to apply this formula to this deflection where your E is normally distributed with mean mu E and standard deviation sigma E, we can take a logarithm of this, and using this logarithm you can put up the value of the value of mean of E. You can figure out the value of mean of log D, and then you can take the inverse log and figure out the mean of displacement deflection. So once you do that, this is how you will get the deflection of rod and corresponding standard deviation once you apply these two formula to this simplified expression. Okay, so this is how we account the effect of randomness on the response of a single bar where only one element or the one variable is random. And we have the closed form solution, so we can use this to figure out the deflection. Now, let's say I'm going it further. I want to evaluate the deflection of the same rod having length L and cross-sectional area. But now I have two random variables. I have variation in inelasticity, as well as the load that I am applying is also not constant. It is also varying. So I have the mean and standard deviation of modulus of elasticity, and I have mean and standard deviation of the load. So both these two are, I can say, the random variable, normal random variables. So how do I figure out the deflection now? How do I figure out the statistics of deflection, which is the mean deflection and standard deviation of the deflection? Again, the mechanics gives me this formula. If I take the log, this is what I get. And now the deflection or this distribution parameter of deflections are depend upon the distribution parameter of modulus of elasticity and that of the load, which is mu p and sigma p. So if you apply the same formula which you have got, you get again the mean and standard deviation of deflection under these two random variables. Now the question is, what is, if you compare the mean and standard deviation of deflection in question number 2 and question number 1, what do you think, what will happen if the load and modulus of elasticity both are random variable? Will it gives the same mean? And if only one, that modulus of elasticity is only random variable, will it give the same mean and same standard deviation? So if you compare that, if you look out the formulation, particularly the standard deviation, it is the sum of square of standard deviation of independent variables, which is in this case modulus of elasticity and load, while the mean is simply the summation of that of the mean load and mean modulus of elasticity. So because of that, the mean doesn't change. However, since there is an additional variation in the load in the second question, the overall deflection or the overall distribution of deflection changes in second question. So both in question 1 and question 2, the mean value of deflection is constant. However, the standard deviation of deflection is lesser in first case or in first question, and it is more in the second question, because in second question we have considered the possible variation in modulus of velocity as well as that of the load. So because of that, what we can say that as the number of variables in which there is a variation, or the number of variables which can be defined using the probability density function, then the outcome variable has larger variance. Now let's say I have used the same rod in a portal frame as a bracing element, and it is subjected to ground motion, and this ground motion gives me the axial compression and axial tension in the bar. Okay, now I know the characteristics of ground motion. Okay, now load is seismic excitation, which is into the bar, and my modulus of elasticity is random variable. Now, how do I figure out the load which is coming onto the structure under earthquake ground motion? The way to do that is the linear time history analysis, but again, it won't be possible to do it for all the situation. So my question is, if you want to figure out the mean and standard deviation of the deflection under this earthquake excitation, how do you use the closed form solution? Because there is no closed form solution. You can't have the closed form solution to evaluate the load in the bracing element because of earthquake load, because as we all know, the earthquake load is transient in nature. Its magnitude is not known, and it's very difficult to figure out the loads which are coming because of the earthquake loads. So what we do is the numerical analysis. So the similar kind of analysis is being used to figure out the statistics of the deflection, and those are called statistical simulation technique. So what we do in this is we take a one value of E, which is a modulus of elasticity that represents the modulus of elasticity of rod, and then we apply the ground motion, and then we figure out the deflection which is coming out, and using that one deflection value, then we change the value of E, and then we figure out the deflection again. So we do it for various values of possible variation of E, and then we obtain the statistics of this deflection. And once we have the large statistics of deflection for various values of E, we plot them, which is called the distribution fitting, to obtain the statistics of the deflection. So this is what again we obtain through the same process. Again, since your E is normally distributed and then there is no other random variable, your deflection is always normally distributed with mean mu delta and deflection sigma delta. And using this, you can always figure out the cumulative distribution function, which is the integration of this curve in the domain between 0 and 1, or sorry, between domain 0 and x. Okay, now let's go it further. Now, instead of applying one single ground motion, if I apply various different ground motion, those are available or those are recorded. There are many ground motions recorded. Now, how can you improve? How can you predict the possible variation in deflection? So the same algorithm that we have seen in the previous slide, we can use that. Where you select the one value of U, one value of modulus of elasticity, you apply one ground motion, you calculate the deflection. Then you apply the second ground motion, you calculate the deflection. You do it for all available ground motions. Then you change the value of E and then redo this process again. So once you have done this, you have large statistics of deflection. And if you plot those, and if you fit a normal distribution, you will get the mean deflection and standard deviation of deflection for all possible ground motion. So that is called the statistical simulation techniques. Now, if you again compare the distribution which you have obtained from question number 4 and question number 5, the question number 4 is for one ground motion, and question number 5 is for large ground motion. Then again, the mean value could remain same, but the standard deviation will be a lot in question number 5, and that's mainly because the ground motion that you have will have various characteristics, and it can impose a large variation into the deflection. So what do you get from this? That when you are considering an uncertain event, and when you don't know what is the possible, what is the amount of force that has been imparted by that random event onto the structure, it poses a large uncertainty in the response of the structure. So when I'm saying my standard deviation is large, it means that my structural response is highly uncertain. And when structural response or structural behavior is highly uncertain, we need to ensure that we are designing it for higher forces or lower capacity bounds to ensure that it has least chance of getting collapse or least chance of getting damage during an earthquake. So this is the cumulative distribution function for these two uh, probability density functions. And as you can see that these two curves intersect for at probability 0.5. That means the mean of both these curves is identical. However, the blue one has larger spread compared to the red one, indicating that the blue curve having a larger variation of response, which in this case is deflection, compared to the red curve. So coming back to the question where we started the probability study, we are circling back it now, that when a building, actual building, is subjected to earthquake ground motion, and if you can relate this with the simple example that we have seen, we can say that my load is uncertain, which is my parameter P, or equivalent to parameters P. And then the second, my resistance, which is my modulus of elasticity, is also uncertain. And since, as I said earlier, we have discussed that with reference to performance-based design and code-based design, since I'm getting into the inelastic range, my load and capacity has to are dependent upon one another. And because of that, you can't estimate them separately. You need to do the simulation that we have seen in the previous slide, taking one value and doing the analysis again and again. This sounds very simple when it comes to simple formulation, which we have seen. However, when it comes to earthquake ground motion, you need to understand that estimating inelastic response is very tricky business. There are various mathematical parameters which are involved in modeling and finding out the inelastic response of the building. Some of that I will cover, but the discussion that I'll be doing today is simplified version of the actual simulation and actual inelasticity that occurs in the structure. So first of all, let's understand how do we statistically, how do we model the seismic hazard? How do we probabilistically model the seismic hazard? Because as we all know, earthquake is a very uncertain event. It originates at the fault, and then the seismic waves travels from the fault across the bedrock towards the base of the structure, and then these seismic waves are further their nature is further changed because of the soil, and when it comes to site at the building location, the building response that we get is also very uncertain because of the inelastic capacity. So earthquake seismic hazard specifically has three parameters. One is source parameter, second is path parameter, and the third is site parameter. So if you really want to understand if you really want to figure out the probabilistic model for seismic hazard, the uncertain variables, those are involved in the calculation of that are seismic faults, because we don't know the exact dimension and the location of seismic fault. Those are always approximated. And the seismic fault maps are generally obtained through the surveys or also through the satellite imagery. And then we don't know the rate of occurrence of earthquake, because as we all know, the various faults are there in the earth crust, and those are displacing, and that causes the earthquake. but we don't know the rate at which those faults are moving. We don't know the exact rate. Just like our modulus of velocity, we know the certain value, and then we can say that there is a large variation. So the rate at which those faults can create a magnitude is not known. The rate at which the rate at which these faults can contribute in terms of the intensity of earthquake is also not known, which is the magnitude of earthquake. So if you have a fault which is, let's say, uh, in the Himalaya, and even if you know the geometry and the rate, we don't know how much magnitude earthquake it can cause. So at max we can predict that this is the possible magnitude and there is a possible variation to that magnitude. So we don't know the amount of rupture that will undergo. And in addition to that, since we don't know the location of fault, we don't know the distance, exact distance between the fault or the location of earthquake and that of the location of the building. In addition to that, the equation which are used to figure out the spectral acceleration, which is of our importance at a given site, are also very uncertain. In addition to that, as I explained earlier, when these seismic waves or this ground motion strikes to a building, it undergoes vibration and it undergoes the inelastic deformation. So the uncertainties, those are involved in figuring out the capacity. First of all, we don't know the amount of force. Then we don't know what is the exact behavior of the material in inelasticity. You need to understand that the modulus of elasticity that we have seen is the linear response, which is much more sophisticated than the inelastic response. So variation of structural strength in inelastic phase is more than the variation of structural response in the linear range. In addition to that, the mathematical model that we use, they also impart certain kind of uncertainty. This uncertainty is called secondary uncertainty, or which is called the epistemic uncertainty, if you follow the nomenclature. So as I was saying, there are these two uncertainties related to demand and capacity are classified into two Yeah, can you hear me?
Yeah.
Yeah. Okay. So as I was saying, the uncertainties associated with seismic hazard, you could say it's aleatory uncertainties, while the uncertainties associated with the structural response, you could say it's epistemic uncertainties. This is a broad classification. Again, aleatory uncertainties cannot be reduced because we will never know the exact fault line and the possibility of earthquakes. While the epistemic uncertainties, like the structural capacity, we can know because we can do the structural testing of various building configuration in the laboratories, and that's how we can reduce the epistemic uncertainties. We can also propose new mathematical model to figure out the response of a structure in non-linear range. So to some extent, we can reduce the uncertainty associated with the capacity, but the uncertainty associated with the seismic hazard is not possible to reduce, and we need to account that when we are evaluating the seismic risk. So this is the common quote which is given by professors from Stanford, where we say that the only way we can predict the performance of the building to possible predicted way is by reducing the uncertainties associated with the capacity. And that's the reason whole science of earthquake engineering is very important, where we test various kind of configurations of the building, various kind of structural systems, various kind of members in our laboratories to figure out its capacity. Now, let's say by some way, if we can generate a model for probabilistic model for hazard and that of the capacity, which is called the fragility. So the probabilistic model of capacity of building at collapse is called fragility function. So as we have seen that once we are defining these two variable as an independent variable, the extension of the conditional probability is the risk is product of these two variables. Okay, and we are interested in figuring out the probabilistic formulation of hazard and probabilistic formulation of collapse, which is fragility, to obtain the risk value. This is what of our importance in today's discussion, where we are discussing the probability of risk. As I said earlier, risk matters for a single building and the loss term matters for a group of building. So the second term that we require is loss, which is the product of hazard, vulnerability, and exposure. Exposure is the thing which depend upon the socio-economic structure of that particular region. I'm not discussing the loss in this lecture, so I'm not discussing the loss parameter to a greater extent. So this is the formulation to figure out the seismic risk. Don't get overwhelmed by the formulation. It looks scary, but it is all having the simple meaning. And most of the terms that we have seen are directly related to this kind of formulation. Only thing is that this is more expressed in terms of the mathematical formulation, and the discussion that we had is more kind of a qualitative or subjective discussion. But the meaning of this mathematical expression and the meaning that we have seen for the deflection of a rod under uncertain or under variable modulus of elasticity and uncertain load is the same. So what we say that the load, in this case it's a seismic hazard, is obtained by integrating the uncertainty associated with various parameters. So this is nothing but the total probability theorem for calculating the seismic hazard. Likewise, I can have a possible variation in collapse, considering the all possible variation in its capacities as well as the deformation. And that is how I obtain the structural vulnerability or fragility. The meaning is same. So both these are obtained through total probability theorem. And when you want to figure out the collapse, that's again you combine these two different formulation. Again, apply the total probability theorem. That's how you obtain the total probability of collapse under given seismic hazard using this particular integration. So the formulation that we have seen, that when you have two variables which are varying, you choose one variable, you choose one variable, you choose value of second variable, you do the analysis, then you keep the first variable constant, change the value of second variable, do the analysis, do it for entire range of first variable, then change the second variable to second value, do it again and again. So once you do all kind of those analysis, that is exactly what has been given through this long formula over here. That is this exact statistical simulation that we have seen so far, and that is expressed as this mathematical formulation. So that is how we calculate seismic risk of a building. So this is a method that is available. What we can do is we select a structural configuration. We do the nonlinear modeling, meaning that the model which can predict the nonlinear response of the structure. Once we have that, we select one ground motion, we apply it to structure, then we change its intensity till the time the structure get collapsed. Then we save that data, we select a second ground motion, we apply it to structure first time, find out its response, again increases intensity, find out the response, and do it for a large number of ground motion. We find out the fragility functions for a given seismic hazard, and we find out the risk. So that is the general procedure. I will again show you that in next couple of slides. And then once we have that, the application of risk is to figure out the loss or risk of individual building and loss to infrastructure. The risk is very important to figure out the rationalized design parameter, which is response reduction factor in our case, because you need to understand that larger the response reduction factor, lower is the seismic force, but then you need to have a engineering judgment to have a larger response reduction factor. That engineering judgment will be provided by this risk formulation. And then the third is uniform risk hazard curve, which is to ensure that the buildings which are defined all across India or all across subcontinent, let's say if those are residential buildings, so the residential building located in New Delhi and residential building located in, let's say, Hamirpur, they should have the same probability of collapse under earthquake. So that is the target that needs to achieve, and that is possible through this risk formulation that we have seen. Okay, so I will move to the first application to figure out the seismic risk. Before we do that, that is the last part of my presentation. Before we do that, any questions regarding content that I have covered? You can ask anything that you have in your mind. Any questions? Okay. Okay. If not, then I'll move to the last part of the presentation, which is figuring the collapse risk. Again, it is linked to the first part, which is our objective. How do we figure out the collapse risk of a building? And the region where I am getting into now is bit of mathematical. It's very difficult to actually correlate all these mathematics to a simple analogy. I'll try to do that, but if you don't understand any part in this, please feel free to ask your doubts and questions. So as I was saying, the ground motion has variation, and this is the typical variation in spectral acceleration. So if you measure a spectral acceleration at various distance for a single earthquake, you can see that even at a same distance, there is a possible variation in the spectral acceleration. It means that my ground motion is uncertain. So seismic hazard definitions are calculated using probabilistic seismic hazard assessment, and it has been expressed either in terms of the peak ground acceleration or in terms of the spectral acceleration. There are ways. I have already mentioned PSHA. There is another method which is called deterministic seismic hazard. So the probabilistic seismic hazard is based on the principle which is called Poisson distribution, and it says that the probability that the shaking will exceed a certain level at least once in a given time. So the occurrence rate is obtained from PSHA is number of events per unit time that can be occurred is given by the occurrence rate. So this is the formula for Poisson's process, and since my hazard is Poisson process, the collapse of a building is also a Poisson process. So here lambda is occurrence rate, like it gives me a number of events per unit time. So if I can say that the probability of happening a large earthquake is 2% in 50 years, then I can work out the lambda using this formula. So if my probability is 2%, which means my p-value is 0.02 and time is 50, the lambda value is 2.03 into 10 to the power minus 3. So if you inverse the lambda, you will get the return period. So if my probability of exceeding certain spectral acceleration is 2% in 50 years, so t is the time variable that I am having, which is the 50-year period, which is my design period, then the return period of that earthquake is 2475 years. It means that that earthquake can strike my building once at least once in 2475 years or 2500 years. This is the standard deviation definition, which is called maximum considered earthquake. So if you are designing a building for MCE, it means that during its lifetime, it will probability of experiencing an earthquake is 2%, or the magnitude of very large earthquake is having return period of 2500 years, but that will happen at least once in the design lifespan of the structure. Okay, this is the step to calculate the seismic hazard using probabilistic method. As I was saying, all the variables are uncertain, and you can model the sources, you can model the distance, you can model the possible acceleration at a site using probability density function. Again, all are not normal distribution in this case. And when you combine all those using total probability theorem, you get the annual rate of exceedance for various values of peak ground acceleration. So once you know the peak ground acceleration, you know the rate at which it is occurring at the site now. Again, this is the total probability theorem which we have discussed. Don't get into the mathematical expression. It looks scary, but it conveys the simple meaning that we have seen. So the second part to estimate the collapse risk is to figure out the inelastic response of the building. And to figure out the inelastic response is a very critical and very interesting area in the structural engineering, where you model a structure using certain ways to figure out the inelastic capacities. So all we have is stress strain curve of the building or stress strain curve of the material. But the building is not constituted only by the material, it is constituted by the element. So there are various levels at which the structural modeling can be done. The simplest one is called the line element model, in which you are not actually modeling the material, in which you are modeling the behavior of the structural element. So this is the example in which the column is modeled as a line element. The line element is nothing but the Euler-Bernoulli beam equation that you have seen, which gives you the formula for deflection. So I hope all of you knows the formula from Euler-Bernoulli beam equation, which is m by I equal to sigma by y is equal to E by R, where 1 by R is your curvature. And once you integrate the curvature, you get rotation. And once you integrate the rotation, you will get the deflection. So that is the basis of this line element. And then the inelasticity, which is material inelasticity, which is now transferred into the inelastic rotation or curvature, is represented using those plastic hinges. This is the hinge which shows the inelasticity in the building. Again, as we have seen, like material deformation, material stress strain curve, we have force deformation relationship for the member. And this is the typical curve that we have, where you have yield point, you have capping point, and the ultimate point. Again, the capping is additional point which is defined to define the geometry of this curve. And that is how you define the behavior of the inelastic behavior of the member. So as I was saying, as we have seen the hysteretic behavior of reinforced concrete element, these are two examples, and the black line over here shows the prediction from the mathematical model. So whenever you are using an inelastic model, you need to calibrate it first. So there are ways to do calibration. So if you can see that the red one over here is the actual hysteretic loop which is obtained from the experimental study. So in experimental study, we actually cast a reinforced concrete column, and it is subjected to incremental load in laboratory, just like a pushover analysis that we have seen. And it is pushed into the inelastic range and then again taken back and pushed in the other direction. So this cyclic is been done over and over till it reaches the ultimate point. So the red curve over here is the observed hysteretic curve, and then the blue curve is the fitted experimental curve. So as you can see that the experimental curve, the predicted curve, the blue one, is matches well with the experimental prediction. It means that the analytical modeling that we are doing is good enough or accurate enough to predict the experimental response. So this is what we have seen over here. And this is the incorrect calibration, this is the correct calibration. So the model which gives you the correct calibration shall be used to figure out the response. This is another example which I have done myself, where the same hysteretic model, which is observed during experiment. I have done the modeling in a software which is known as IDARC, and using a moment rotation relationship, I was able to figure out the hysteretic parameters. Now the black line is the experimental response and the red one is my prediction. So there are some errors, but again, this is not very bad calibration. This is a moderate to good calibration. So once we calibrate our analytical model, we can use them to predict the response under earthquake ground motions. So having said that, again, it is very important to calibrate the response which are obtained from to calibrate the response of the entire building system under ground motion. Again, it's very difficult to find out response of actual building subjected to ground motion because there are no such studies available. And in addition to that, there are many other variations, which is called soil amplification issues. So to ignore that, there are certain experiments which are carried out on the shake tables, where a small scale structure, a small scale model of a actual building is constructed over a shake table and it is subjected to ground motion. And then the experimental damage pattern is observed. Now I have got the data of such experimentation. I have modeled that building analytically, and then I applied the same ground motion to my analytical model, which has been applied to a experimental building. And then I compared the analytical study with the experimental study, and I observed that the analytical damage, the predicted damage from my model, matches well with the experimental observations. So these are again the comparison of analytical and the experimental studies. Again, if you can notice that there is not the exact match between analytical and the experimental study, the analytical study is slightly distorted than the experimental. But this thing doesn't matter much, because when it comes to collapse, I'm always interested in the peak response. So my peaks are matching to a good extent than my overall time history. So my model is calibrated. So this is the comparison. This is the experimentally predicted response, and this is the response which I have got from the analytical model. So you can see that analytical model predicts the experimental response to greater accuracy. So once I have the analytical model, as I said earlier, to figure out the fragility function, I need to do a nonlinear time history analysis, and there are methods to carry out the fragility, to develop the fragility function. So once I have the analytical model, I carry out the nonlinear time history analysis. For each applied ground motion, I increase its intensity till the point the structure get collapsed. And for each analysis, I figure out the capacity curve, which is called IDA curve, incremental dynamic analysis curve. Since this is the nonlinear time history analysis, we are not calling it as a capacity curve. The capacity curve is purely obtained from the pusher analysis. So this is the example of that. I have a structure subjected to ground motion, and for single ground motion, I increase the intensity, and then I measure the maximum story drift in the building. Once I'm done with the one analysis, I again increase the intensity and obtain the second maximum story drift. So each blue line over here represents the time history, nonlinear time history analysis carried out for one single ground motion. Now, once I'm done with the one ground motion, I change the ground motion, I choose another ground motion and do this again and again. So all this blue line represents analysis for various ground motion. And then I choose the value at which I define the collapse of a structure, and at which all these possible variation in spectral acceleration, which is the demand, gives me the fragility function. So this is a definition of fragility function, where the capacity is exceeding for a given intensity, and then I have then it has been calculated by fitting the log normal distribution. As we have seen that the analytical model doesn't accurately predict the experimental response. So the variation that we observed in the analytical study are lesser than those are possible in the field. So because of that, we need to account the variation in the analytical modeling, which is the epistemic uncertainty. So the beta total that we obtain is a combination of variation obtained from this curve and variation which is there because of the mathematical modeling. So once you're done with the capacity curve, this is the example of the incremental dynamic analysis, where the red one curves represent the mean capacity, and blue and green one represents the possible bounds at mean minus sigma and mean plus sigma probability levels. Okay, so once you got the fragility function, you can this is the fragility function looks like. You have the collapse probability against the spectral acceleration. This is how it looks like. And knowing the spectral acceleration, you can figure out the probability of collapse. So this is how you can evaluate the risk. So knowing at the site what is the possible spectral acceleration that is coming, you can figure out the collapse probability of the building. However, having said this, we all know that earthquake ground motion, because of its nature, is not certain. There is several variation to it. And because of that, the risk that we calculated, just a second. Sorry about that. So, as we have seen that my amount of spectral acceleration or peak ground acceleration at a site cannot be predicted accurately. It is also the uncertain variable. So I need to account the probability of that acceleration as well. So to figure out the expected failure rate or expected collapse rate of a building. So this is the formulation which is available. In this, again, you take up a one value of spectral acceleration, you take up the corresponding probability of collapse, and then you integrate that over various values of spectral acceleration. Once you do that, you get the expected rate of expected collapse rate, and then using the Poisson's formula, you can figure out the probability of collapse in given time. So knowing the design lifespan of the building and knowing this rate, you can figure out the probability of collapse. So this is the example that I have taken. Let's say this is my seismic hazard at a site, which gives me probability of exceedance in 50 years against the ground acceleration. This curve I converted into the annual rate of exceedance using a Poisson distribution formula. And then I take the annual rate corresponding to each peak ground acceleration. So I had divided this corresponding to each ground acceleration, which is nothing but the slope of this curve. And when this is, I'm considering the fragility function, which gives me the annual rate of exceedance of the collapse against the peak ground motion. So for the building which we started with, a single building which is designed as per IS 1893, we have carried out the fragility analysis. We have figured out its fragility curve, and using this fragility curve, by convoluting these two, we have figured out the total collapse risk. So the total collapse risk that we have obtained is 0.68%. And for 50 years of design span, the probability of collapse is this, which is 6.78 into 10 to the power minus 3. Now, is it acceptable or not? So our code doesn't talk about the collapse probability. So we have we refer to ASC 7, which gives us the expected collapse risk of a building for various occupancy class. So as per this code, when your importance factor is 1, which is for most of the residential and commercial building, it should have the probability of collapse at MC hazard level to be 10%. And what we have got is 0.0678, which is less than the 10%. So our Indian code design, when it designs a building, when we design a building as per IS 1893, then it ensures that the building is not collapsing at MC hazard level. So this is what given in second level performance based design, in which this kind of procedure, the fragility functions are used to figure out the response reduction factor. I'll quickly go through it, where The response reduction factor is expressed as the complex combination of nonlinear capacity, their buffer strength, reduction in seismic demand. So if you can relate the response reduction factor with ductility only, now it is being related to the overstrain factor, which is the additional strength that you consider when it comes to rare events like an earthquake. Uh, in addition to that, there is a possible seismic demand because your time period is increasing once structure is getting into the inelastic range, and through that you reduce the amount of forces those are coming onto the structure. So this procedure is given in a document which is called FEMA P695. These are the response reduction factor given in IS 1893. These are the response reduction factor given in various code. So if you look out IS 1893, the response reduction factor for ductile reinforced concrete moment resisting frame is 5. However, that is given in ASC 7 is 8. So ASC 7 actually having the larger response reduction factor compared to IS 1893. So does that mean that they are designing it for lower force level? The answer is no. Their seismic hazard definitions are actually based on the probabilistic study. In IS 1893, the seismic hazard that we have is the combination of DSHA and PSHA. So because of that, the response reduction factor that we obtain is very much different than the ASC 7. And then there is a need to rationalize all these parameters, which we are doing through this document, which I just mentioned, which is quantification of building seismic performance parameter. It is again published in United States, and the document is FEMA 695 numbered. So this is the method. I'm not discussing. We are short of time. So this method will help us to figure out the good values of R that ensures that the collapse risk is very marginal. Okay. There are parameters. Again, I'm not discussing that. This is much more to digest in one day. So I will leave you up to this. And there is a great deal of research going on to figure out the values of R as a combination of overstrain factor and considering the energy dissipation characteristic. So in addition to that, the other important topic in earthquake engineering is to use the supplementary energy dissipating devices to improve the seismic performance. That's again useful to reduce the collapse risk. So the framework that I have discussed so far, the application of it is in not only related to the design, it is also very useful in the seismic assessment of a building. Okay, any questions?
So if you have any question, please ask Dr. Saurav.
I know this is a bit too much to cover up in 2 hours because this is bit mathematical.
Right.
I try to simplify many things, but I understand it won't be possible to put light.
Yes.
Yeah.
We
So
will
yeah, please go
go
ahead,
on
and
research.
anything you want to discuss, I'll be more than happy to answer.
I feel that uh, nobody wants to ask any question.
Okay.
Anyway, Dr. Saurav Shirodhankar is also available through email. So related to this topic, or even if you want to carry out your research work in this area, you can also uh, mail him and get his idea or point of view.
Sure.
So
That would be good point. I'll share this entire presentation with you. So you can
right, it
refer
will be
to it.
very
And
helpful.
yes, and if you have any question, please let me know. I'll be more than happy to discuss. Because this is relatively new subject. Again, estimating capacity of a building
Right.
is known to a greater extent. I haven't covered that much that in detail in this presentation, but I tried to throw some light about the probabilistic calculation, which is essential to know because we will be moving towards that kind of design procedure in next 3-4 years. So I hope all of you got something out of this. Uh, yeah, yes, Joy.
Yeah, it was really, really very interesting and full of information related to. Sir, you started with really from the very basic level, like evolution of earthquake design, and then covered the basic part of earthquake design, then performance-based design. You also discuss about the collapse risk you were discussing, and when it was required to go to the basic level, you also covered that one. So I it actually going on. So I feel that the participants who are really interested for the research or higher study, they can get idea or they can get I hope that they can build up
Your voice is breaking. Sorry, so I'm not getting many things.
seismic risk targeted design. Uh, I thank you once again for your presentation and for your talk. And I hope that in future also we will get the same cooperation from your side. Thank you very much.
Yeah, thanks a lot, Joy. Thanks a lot, organizing committee. It's been pleasure talking to you. Again, I'll be more than happy to cover more basic topics. Since the topic of this course is advances, I get into the risk framework. But if you plan some basic programs, then I'll be more than happy to cover the basics. So thanks a lot
Yes,
again
yes.
for joining me. It's been great connecting to the young mind. Thank you.
Thank you, sir. Thank you. Okay, so sir, you may disconnect.
Thank you. Thank you.
No problem. So will be our next lecture will be starting from 3:30. Uh, so we'll meet again at 3:30 with the presentation of Dr. Sandeep Chaudhary from IIT Indore.
Good afternoon, sir. Sir, your mic is muted. It's muted.
Yeah, good afternoon, Vimal.
Sir, there are still 19 participants have joined, so we will wait for 2 3 minutes.
Okay, okay.
We will start. Can we start, sir?
Yeah, Vimal, just 1 minute.
Okay, sir. Okay.
Yes, Vimal, I think we can start. Yeah.
Okay, sir. So, good afternoon, ladies and gentlemen. I am pleased to introduce our renowned speaker for this lecture, Professor Sandeep Chaudhary ji. He is currently working as a professor in Department of Civil Engineering, Indian Institute of Technology, Indore. Before joining IIT Indore, he served as a faculty member in different capacities at MNIT Jaipur. He has about 25 years teaching academic and research experience. He completed his Bachelor of Engineering from MBM Engineering College, Jodhpur. He completed his Master of Engineering from Malvi and Regional Engineering College, Jaipur in 1999. He completed his doctoral PhD from IIT Delhi in 2006. Also, he did his postdoc research. He was a postdoctoral research fellow in Structural System Laboratory, Korea. He supervised 9 PhDs and 35 postgraduate students. At present, 6 students are doing their doctoral research under him. He has published more than 75 research papers in journals and more than 50 research papers in conferences, and also published 4 patents. He has handled more than 10 research projects and more than 150 consultancy projects. His area of research interests are structural engineering, sustainable construction practices, composite bridges, novel bricks and blocks, microstructure and durability of concrete, advanced characterization techniques. Now, I would like to request Professor Sandeep Chaudhary sir to share his views with us. Sir, please.
Yeah, thank you, Vimal, for the introduction, and thank you for inviting me and giving me a chance to interact with all. And for next about 90 minutes, we are going to discuss a little bit about steel concrete composite structures. I split the presentation in 2 parts. The first part, that will be sort of a basic presentation on steel concrete composite structures, that what are the advantages, why do we use the composite structures, and then we'll move to more advanced topics, particularly about the shear connection behavior. So I think I can start. I think the screen is visible now. Yeah, the screen is visible now.
Yes, sir, it is visible.
Okay. Okay, so in about first 25-30 minutes, let's discuss a little bit about steel concrete composite construction. And I had picked up this topic because the reason it was written there, advances in structural engineering. And this is one of the upcoming areas in the construction. And the importance of this area is, though it has picked up well in other countries, but in our countries, somehow still there's a big gap in the field and in the research area also in this topic. And there are a lot of opportunities to build research career in this particular area, but still there are wide gaps and we have ample opportunities to work upon. So coming down to the steel concrete composite construction, what is the need of going for a steel concrete composite construction when we do have sort of steel constructions also, we do have concrete also.